All right, everybody. Welcome to Unit 4. And now we're going to take what we learned in Unit 3, Atomic Structure, and move on to Unit 4, which is studying the periodic table and the things that go into the trends and the relationships of the elements before we go on to putting it all together in the bonding unit. So, a couple of things about the periodic table to start off, just a little introduction here. And we talk about the modern periodic table just to start off. Okay, and really during the 19th century, and this is going back a ways. Bunch of different scientists began to categorize the elements, and what they did this in terms of their reactivity and their observations with the elements. So really, that was really the interesting thing about this, is that we really didn't have much information, but we did have relative atomic masses or atomic weights, really comparisons of the elements with really hydrogen. Okay, and they really grouped them according to their physical and chemical properties, and really that was the way we started doing this. All right, the end result was this table, this modern periodic table. Now here I show you guys the wide table where the F block is actually in the middle here. So your F block is actually here. So if I change this a little bit just to give you a little bit of a different thing here. Okay, your F block is actually in the middle here. Here's your D, right? Your P block is here, and your little S block is here. So again, later on, what we did is we took the F block and moved it, took this out, moved it to the bottom of the table here, and then moved everything together. So now you have your S, your P, your S, your D block is here, your P, and your F at the bottom. I just show you what the wide periodic table looks like. Okay, here's a little iodine. This is iodine. Okay, this is sodium, the reaction of sodium plus chlorine here in this reaction here. Okay, again, iodine crystals really are, iodine is a solid and they sublime to iodine gas. Okay, this is really oxygen, liquid oxygen. And something interesting with the liquid oxygen, if you pour it through a magnet, it actually sticks to the magnet. It's interesting. Okay, and we know mercury, Hg, okay, has these little liquid balls. Okay, and these are liquid, and you can actually break them and put them together. And once you put them next to each other, they'll actually come together and form a liquid. So just looking at some of the elements in the table, again, an idea. But again, when we first started looking at this periodic table back in that time, we really didn't have a way to categorize them into this table. So we take a step back into time where we look at Dmitry Mendeleev, and he gets a lot of credit, or most of the credit, for really putting together the main table that we see today. But there were scientists that started to get pieces of this based on the relationship of the elements. They would categorize them based on reactivity and come up with different ways they can do it. And I'll show you this in the little video we're going to see. All right, so Mendeleev was a Russian scientist, basically famous for creating the first periodic table and really put it together for increasing atomic mass. And he would put these together by atomic mass, but also put them in columns that had similar chemical properties. All right, now the key, though, what was great about Mendeleev, all right, was what he did is he saw these breaks in the table where there was breaks in atomic mass. So instead of putting those elements together, he would leave these blank spaces in the table where he predicted undiscovered elements would fit. So he believed that in these spaces there were elements that belonged there, but we hadn't yet found them. We hadn't yet found them yet. And this was kind of a bold prediction at the time, because you could have easily, told him that, no, we could put these elements together. Why are you leaving spaces? But he believed there was elements out there. All right. As a little bit of an interesting thing, he predicted silicon. Now, ecosilicon means after silicon. So he was actually looking at the element underneath silicon. So if you looked at silicon in the table, you would see that it would be silicon here. And then what Mendeleev did is he left a blank underneath that. So you would have the element here, and then this would be a blank. He predicted this element, this mystery element, ecosilicon, to have an atomic mass of 72, density of 5.5, a dirty gray color, and so on. And he believed the oxide. So he believed again, ecosilicon would be, this symbol would be ES. Okay, he believed it would have the oxide of ESCO2, and the oxide would have a density of that. So real specific. If you look down here, some specific data that he predicted this to be. All right, and then 15 years later, in 1886, they actually discover germanium Ge, okay, which ends up fitting in that box exactly how he predicted. So it's really like telling the future, in a way. And again, this is the data that was actually measured. So this is the actual part. She actually measured these things about germanium. So again, right on top, really, really right on target on what these actual, again, you're a little off, but basically right on target from what we really observed. So again, he was able to make these predictions, all right, and he was able to predict them for, gallium and scandium and germanium, and they were almost complete matches with what he predicted. So this propelled Mendeleev to be a really high level with his table, and it was adaptable, right? They would find elements and they would fit in these spots. All right. So I'm going to show you a little video on that in a little bit. Now, if we move on, just a little bit later than that was Henry Moseley, and we'll see that Henry Moseley, unfortunately, died real early. You're talking World War I here. Okay, Moseley ends up going into the war, signs on as a soldier for the British Army, and ends up getting killed on the front line. So a tragic story for a scientist, in a British scientist, again, very young age. All right, what Moseley was able to do is he working with X-rays. He actually worked with Rutherford in Rutherford's lab. Okay, and he worked on a project playing around with X-rays at the time, and he was able to they were able to develop X-ray spectra for the first time, and he ended up discovering the atomic number of the elements, which is the number of positive charges in the nucleus. He was able to kind of, get data based on this, and he realized that the properties in the table were not by atomic mass, like Mendeleev thought, but they were more of atomic number, okay, and not atomic mass as Mendeleev previously thought. So he really solidifies the table as the elements going one by one for atomic number and not atomic mass. Okay, where Mendeleev was more of an atomic mass and properties guy, this solidifies the relationship in the table. All right, and again, that's what happened. So if you take a look at this, this is Moseley's, quote. Here's Moseley working in his lab. And an interesting thing about atomic mass here, as you can see in the table, that you might see why Mendeleev had a little trouble with this, is that when Mendeleev would column his elements by type, or for instance, if you took a look at tellurium and iodine, the mass actually goes up with the elements. So if you take a look at gallium is 69, 72, 74, 78, 79, 83. You go to the other side of the table and you can continue, right? We take 114, 118, 121. Then we go to 127 and something strange happens. This is 127 and then it goes down to 126. So it goes down to 126 and then back up to 131. So Mendeleev normally would have switched these if he was going with atomic mass, right? 126 would go here and 127 would go there. However, Mendeleev had the right idea is to keep those elements in the same row that had similar reactivity. Okay, and he stayed with that. But this really bothered him. But even though it bothered him, he stayed with this idea. And as long as he stayed with that idea, then the elements would line up in their specific spots, and that was what was most important to him. It was Moseley that ended up coming up with the fact that it was not the atomic mass that kept them in this way, but more the atomic number, that when you went from 51 to 52 to 53 and 54. All right, so that's the achievement of Moseley. Unfortunately, Moseley was killed. He probably would have won, or they believe he would have won the Nobel Prize for this, but unfortunately, at such a young age, it was actually quite tragic. All right, so just the periodic table in general, really quickly. Again, I'm going to go through this very fast, and I'll put the video on, let you watch it because it's interesting stuff about Mendeleev. Okay, so group one really is called the alkali metals. Okay, you've probably heard this before. Group one is here. Again, hydrogen is here, but hydrogen is not a metal. Okay, just make sure you understand that. Important stuff about hydrogen, that this is not a metal, so hydrogen would be here. Okay, helium is here. Okay, hydrogen is going to be not a metal, so really important. It's not part of. We put it as part of this because of the valence electrons, but hydrogen is not a metal. All right. Number two would be the alkaline earth metals, would be group two. Okay, group 3 through 12 here is the transition elements, anywhere from 3 through 12. Okay, groups 13 through 16. Is your other non-metals and other metals. Again, it's named after the families of the elements. So if you want to think of it like, It's named really after the members, so that we can call this the boron family. This is the carbon family. This is the nitrogen family. Okay, nitrogen. Okay, and this is the oxygen family. And this would be all families of these elements. Okay, so boron family, carbon family, nitrogen, oxygen family. Okay, group 17 would be the halogens. Okay, which means salt former. Okay, and we know the noble gases again would be, or sometimes we call these inert gases. Inert gases, sometimes we call them. Okay, we've been seeing those lately. All right. Now, don't forget your periods are the rows or the energy levels being filled at that point. Again, don't forget your D starts here. This is the 3D level. Okay, so if we go back to what we were talking about in the atomic structure, again, 3D would start here, 4D would start here, 5D would start here. Don't forget, again, we're not going to do much with the F row, but remember that the rows are the outermost energy being filled. Okay. And your same groups, your valence electrons, would be looking down. That's important to know about the periodic table. So you're going to have to know your names of your groups and know what's going on here as we go. All right, so that would be an important part. All right, so we're going to stop here, and I'm going to play this video for you. I want you to watch that up there, and then we'll bring up this here. So sit tight, and I want you to watch the rest of this.
Drafts of Mendeleev's table show plainly the struggle he went through.
The bottom of the page, he lists the elements to be classified. As he fits them into the table on that page, he crosses out the elements. It's just what you and I would do. We can see the effort in that page. He's making mistakes. He's correcting them. It's full of crossings out. There are things that don't quite fit. This is a human being trying to understand this world.
Hour after hour, Mendeleev worked on the table, missing one train after another. Finally, he dismissed the coachman. The cheesemakers would have to wait.
Madame. Alexandra Alexeev приехал.
That afternoon, a visitor found him distraught, unable to capture the order he knew was there, just out of reach.
Now adding more restrictions.
Later that day, Mendeleev came to a choice that would crystallize his thinking. The elements involved were iodine and tellurium.
Iodine's a little lighter than tellurium, so it should come first. But Mendeleev looks at that and says, well, if I put iodine first, it's in the wrong family. It's actually a halogen, which is the next row down.
If he stuck to that weight rule, it would put an element outside of the family it obviously belonged in.
So he decides tellurium, the heavier element, should go first. It always bothered him that iodine was lighter than tellurium but came after. That breaks the order of atomic weights, but it preserves the family resemblances, which are more important than just the increase of atomic weights.
With that principle established, Mendeleev hurried toward the end.
And the more he worked on it, the better it looked.
Finally, that evening, Mendeleev completed his table. Before leaving the next day, he ordered 200 copies printed and sent to leading European chemists.
By the time he left for the cheese factory, Mendeleev knew that he was onto something extremely important. I think he realized that day that he had cracked it.
With a few modifications, soon made by Mendeleev himself, his 1869 draft is easily recognized as the periodic table of the elements, incomplete but unmistakable. In his published table, Mendeleev left blanks for some of the elements he thought were missing.
Not only did he leave a blank space, but he suggested an approximate atomic weight for that future element.
And the fact that Mendeleev on that first weekend is already thinking this way, that's a sign that he believed that there's something deeper going on here.
Mendeleev believed his table was more than a convenient way to arrange the elements. He was convinced he had discovered a law of nature, that the properties of the elements are determined by their atomic weights and vary in a regular, periodic way across the table.
It's periodic because the properties of the elements repeat in a regular fashion. When you wrap around from one row to the next and come back to where you were, the elements that are in the same column have similar properties.
He had an almost mystical feeling that this was there in nature and not so much a human invention as a discovery.
Given the remarkable regularity of his table, Mendeleev couldn't believe nature would have just left some spaces empty.
Laws of nature do not permit exceptions.
There must be an element which we have not yet discovered. Go look for that element.
And he was bold enough to not only to say an element is missing, but to predict.
The periodic law allows us not only to predict what new element will be found, but also to determine in advance their chemical and physical properties.
In 1871, Mendeleev published an article making predictions about 3 of the missing elements, based on the properties of their neighbors in the table.
Chemists really weren't used to making predictions of any kind, let alone ones to this degree of specificity. They are remarkably precise and quite daring for Mendeleev to print them.
4 years later, a French chemist found a new metal so soft it melted in his hand. He called it gallium. It seemed to be a good fit for the empty spot below aluminum, but the density didn't match Mendeleev's prediction. He wrote the Frenchman suggesting that he check his data.
So you can just imagine this Frenchman who actually has the element in his hands, hearing from this Siberian who has never seen the element, and daring to say to him that he's made a mistake.
But sure enough, when the French scientist rechecked his measurements, Mendeleev was correct.
So not only had Mendeleev predicted the element, but he knew the properties of the element better than the discoverer of the element knew them.
Within 15 years, all 3 of the detailed predictions are discovered, and that catapults Mendeleev to chemical superstardom.
I never thought I would live to see my ideas verified. I was wrong.
Ladies and gentlemen, the following
But in 1894, 2 British scientists made a discovery that threatened to bring Mendeleev's carefully crafted edifice crashing down. They found a new gas they called argon that didn't seem to fit into the table.
When Lord Rayleigh and William Ramsay discovered argon, it looked like a problem, a very serious challenge to the periodic table itself.
Mendeleev's first reaction to almost anything that was contradictory to the system was to be hostile to it and suspicious. And Mendeleev therefore decides it's not an element. There are lots of reasons to think that. First, it doesn't react with anything.
Chemists couldn't get it to do anything. It was inert. It behaved like no other gas that anybody had ever encountered.
And secondly, it has no place on the table, so how can it exist?
Matters got worse when Ramsay announced he'd also isolated helium, 30 years after it was first detected in the sun. It was definitely an element, and it too had no place in the table.
And then just 3 years after that, William Ramsay's research group discovered 3 new rare gases, krypton, xenon, and neon.
They display the same kind of properties, they're all inert gases, and they display the same increase of atomic weights as the other natural families do.
And that changed the situation dramatically. What began as a single anomaly, a single puzzle, now looked like a group of elements.
Now we can see that helium, neon, argon, krypton, and xenon are as closely united as any other group.
And so Mendeleev makes the single biggest revision to the system he ever did. He puts in a new column, and that is the family of noble gases.
My periodic system is in no way injured by these discoveries. In fact, they confirm and strengthen it.
It turned out to be a vindication of the periodic system, and if anything, made it even more profound, the discovery.
Mendeleev's table had finally brought order to chemistry's unruly garden.
After Mendeleev, one could see that each element had a place. It was a grand design that worked.
Chemistry wasn't just one thing after another, random substances we've dug up from the earth. They are interlinked in a complicated and rich way.
We are at the dawn of a new era in chemical science, approaching a new understanding of the still mysterious nature of the elements.
As the 19th century drew to a close, the periodic table's ability to corral the elements contributed to a growing sense that the work of science was just about complete. Most of nature's building blocks had been found, measured, and cataloged. Chemists agreed these elements had been and always would be the same, forever fixed, unchanging. All that remained was to fill in the few remaining blanks. Or so it seemed. In fact, this smug sense of satisfaction was about to be shattered by something and someone completely unexpected.